What if the oldest living things on Earth are hiding something we haven't fully understood yet? It sounds like an unusual question. These are trees, after all. They grow in soil, absorb water, respond to seasons, and leave behind rings that scientists count and measure. There's nothing mysterious about a tree, at least not on the surface. And yet, when researchers sit with the data long enough, certain details begin to surface that don't fit as cleanly as the official explanation suggests. Not in a way that overturns everything, but in a way that makes a careful observer pause and ask whether the full picture has actually been assembled. Ancient trees have stood for thousands of years. Some of the oldest known specimens were already centuries old when the first human cities were being built. They were alive during periods of history that exist only in fragments, partial records, collapsed languages, civilizations that rose and disappeared without leaving much behind. These trees witnessed all of it, and in a very real sense, they carry a record of it inside their wood. That record, researchers say, can be read. It can be measured, analyzed, and placed into a timeline. The science of doing this is well established and widely accepted. But what that science reveals is not always as straightforward as it first appears. The general understanding is that ancient trees are extraordinary survivors. They endured because of where they grew, how their biology works, and what conditions surrounded them over centuries. Scientists have studied them carefully and built detailed explanations for why they exist where they do and how long they have been alive. Most of these explanations are reasonable. They draw on real data, real field work, and real laboratory analysis. The scientific community has reviewed them and, for the most part, agreed with their conclusions. None of that is being questioned here. But agreement is not the same as completeness, and completeness is where the uncertainty begins. Some of these trees exist in places where, according to current understanding, they simply shouldn't be thriving. That is not an exaggeration. It is a detail that researchers themselves have noted, often in the quieter sections of scientific papers that don't make it into news articles or educational summaries. The soil conditions in certain ancient tree locations don't match what the species is known to require. The drainage patterns are wrong. The mineral content is unusual. In some cases, the surrounding ecosystem looks entirely different from the zones where the same species grows elsewhere. A reasonable explanation might be that the tree simply adapted over time. But adaptation across thousands of years would itself leave a biological record, and that record isn't always clearly present. Some of these trees also grow in positions that are difficult to explain from a climate perspective. If a tree established itself in a particular location 4 or 5,000 years ago, the climate of that region at that time would have looked very different from today. Rainfall patterns were different. Temperature ranges were different. What was suitable then may not have been suitable for the centuries that followed. Most trees don't simply persist through radical climate shifts. They migrate, decline, or disappear. The fact that these particular specimens held on while surrounding populations did not is something that has been observed but not fully explained. Others show internal growth patterns, visible inside the rings themselves, that don't align with the climate records from the same period. Tree rings are supposed to reflect the conditions of each year. A narrow ring suggests a difficult year, drought, cold, disease. A wide ring suggests favorable conditions. When researchers cross-reference ring patterns with known climate events from historical records or ice core data, they expect to find a reasonable match. And often they do, but not always. Some specimens show growth patterns that diverge from what surrounding climate data would predict. This is sometimes explained as localized microclimate variation. Other times, it is acknowledged as an anomaly and moved past without a clear resolution. A few of these trees have been dated using multiple methods, and the results don't always agree with each other. This is perhaps one of the more quietly significant details in this area of research. When ring counting produces one number and radiocarbon analysis produces another, scientists apply adjustment techniques to reconcile the difference. Those techniques are considered scientifically valid, but they involve judgment, interpretation, and calibration assumptions that introduce their own uncertainties. The final number that gets reported to the public, say, for 1,800 years, carries an implied precision that the underlying process doesn't fully support. There's always a range. And in some cases, that range is wider than most people realize. None of this has a clean explanation. That fact alone is worth sitting with for a moment. In most areas of established science, the unanswered questions are either minor and acknowledged, or they're being actively investigated with visible progress. In the study of ancient trees, some of the questions that have been noted by researchers over decades remain in roughly the same state they were in when first raised. Not because the researchers are uninterested, but because the answers are genuinely difficult to find, and because the specimens themselves are irreplaceable. You cannot re-examine a tree that no longer exists. You cannot go back and take a different sample from a cross-section that has since deteriorated. Researchers acknowledge the gaps but tend to move past them quickly. This is understandable in a practical sense. Science operates on priorities, funding, and available time. A gap that doesn't threaten the core conclusion of a study is easy to note briefly and set aside. But those brief notes accumulate. When a reader goes through enough technical literature in this field, the gaps begin to form a pattern. Not a pattern that points clearly in any one direction, but a pattern of recurring uncertainty that doesn't quite match the confident tone of the public-facing explanations. The general public rarely hears about these inconsistencies. This is partly how science communication works. When a finding is reported to a wide audience, the focus is on the conclusion, not on the methodology's limitations. A tree is 5,000 years old. That is the story. The margin of error, the conflicting sample results, the unexplained soil conditions. These are details for specialists. But they are also details that, taken together, raise questions about whether the full picture is being communicated as clearly as it could be. Most people accept the official age estimates without question, because there is no particular reason to question them. The numbers come from credible institutions, reviewed by qualified researchers, and published in respected journals. That context gives them a weight that feels final, and in many ways, it is appropriate to trust that weight. But trust and completeness are different things. But when you look closely at the data, something feels slightly off. It is not easy to point to a single moment where everything becomes unclear. The uncertainty is distributed, spread across individual studies, small methodological notes, revised estimates, and quietly updated databases. A number changes without announcement. A location gets removed from a list of oldest known specimens without explanation. A paper raises a concern and is cited in 3 subsequent studies, each of which notes the concern but doesn't resolve it. Individually, each of these moments seems minor. Together, they form a kind of background noise that becomes increasingly difficult to ignore. Not dramatically wrong. That distinction matters. There are no obvious fabrications here. There are no researchers claiming to have found something that cannot be verified. The work that has been done is real work, produced by people with genuine expertise and genuine care for accuracy. What feels off is subtler than error. It is more like the feeling that a map has been drawn from the best available information, but that the territory it represents is larger and more complicated than the map suggests. The map is useful. The map is largely correct, but the map is not complete, just not fully settled. And that phrase, not fully settled, is perhaps the most honest description of where the understanding of ancient trees actually stands. Settled enough for most purposes. Settled enough to publish, to teach, to reference in broader research, but not settled in the sense of having answered all the questions that the data raises. Some of those questions have been noted and set aside. Some have been investigated without resolution. Some have barely been asked at all, because the specimens that might answer them are no longer accessible. And that raises a question worth asking. Do we actually understand these trees as well as we think we do? Not as a challenge to the researchers who have spent their careers studying them, but as a genuine inquiry into how much confidence the available evidence actually supports. Science is at its strongest when it holds its own conclusions loosely enough to revise them when new information appears. In this field, some of the information that would allow revision is simply not available. The samples don't exist. The trees have been lost. The original fieldwork notes are incomplete or inaccessible. What remains is a record that is remarkable in many ways and uncertain in others. The uncertainty is not evenly distributed across all questions. Some things about ancient trees are known, with a high degree of confidence. Others are much less settled than they appear in the places most people encounter them. And the challenge is that these two categories, the well-established and the uncertain, are often presented together, without clear markers distinguishing one from the other. This is not a unique problem in science. Many fields face the same challenge of communicating nuance to a public that reasonably expects clarity. But with ancient trees, the stakes of that communication are higher than they might seem. These organisms are used as anchors for climate models, historical reconstructions, and ecological baselines. If the anchor is less stable than assumed, the things connected to it may also need to be reconsidered. That is not a conclusion. It is a question, and it is a question that the data, taken carefully and honestly, does not yet allow a complete answer to. So the mystery isn't found in one dramatic discovery or one unexplained event. It is found in the accumulation of small details that don't quite fit, in the patterns that repeat across different specimens and different studies, in the questions that have been raised and not answered, in the gap between what the public understanding of ancient trees looks like and what the actual research record contains. Something about these trees doesn't match the official story exactly, not in every detail, not in every location, but enough that looking closely at the evidence leaves a careful observer with more questions than they started with. And the most important of those questions may be the simplest one. How confident can we actually be in what we think we know? The official explanation for how we determine the age of ancient trees is, at first, quite straightforward. Scientists have developed a method, a set of tools, and a framework that most people find easy to accept. When the explanation is presented clearly and simply, it sounds complete. It sounds settled. And for many purposes it is. But looking at the full details of how this process actually works, and where its boundaries are, reveals a more complicated picture than the simplified version suggests. The method at the center of this explanation is called dendrochronology. It is the scientific study of tree rings. The word itself comes from Greek roots, dendron, meaning tree, and chronos, meaning time. It is, in a literal sense, the reading of time through wood. The idea behind it is elegant in its simplicity. Trees grow outward each year, adding a new layer of wood just beneath the bark. That layer becomes visible as a ring when a tree is cut or cored. Each ring, in theory, marks one full year of growth. Count the rings from the outermost layer inward to the center, and you arrive at the tree's age. This concept has been understood in basic form for centuries. Even Leonardo da Vinci made reference to tree rings in his notebooks, noting that they seem to reflect the passage of time. But dendrochronology as a formal scientific discipline developed much later, primarily in the early 20th century. It was the American astronomer Andrew Ellicott Douglas who first recognized that tree rings could be used not only to count years, but to read climate conditions. He noticed that rings varied in width, depending on growing conditions. A good year produced a wide ring. A difficult year, drought, cold, disease, produced a narrow one. This insight turned tree rings from a simple calendar into something closer to a historical record. For trees that are still alive, researchers extract what is called an increment core. This is a small cylindrical sample of wood taken from the trunk using a hollow drill. The process is careful and, when done correctly, causes minimal damage to the tree. The core is then brought to a laboratory, dried, and examined under magnification. Each ring is identified, measured, and recorded. The total count gives the tree's age. The width patterns give a record of the climate conditions the tree experienced across its lifetime. That record can then be compared against records from other trees in the same region to build what researchers call a master chronology, a long sequence of ring patterns that extends further back in time than any single tree could provide alone. For fallen or dead specimens, the process is somewhat different. Cross-sections can be cut directly from the trunk, giving researchers a full view of the ring sequence. This allows for more detailed examination than a narrow core sample. Some of the most important dendrochronological data has come from ancient dead wood preserved in dry conditions, old beams in historical buildings, logs preserved in bogs, or timber buried in archaeological sites. These samples can extend the master chronology further back, sometimes by thousands of years. The chain of overlapping records, from living trees to ancient dead wood, is one of the foundations of this science. This method has been in active use for decades. It has been refined, standardized, and applied across many different species and geographic regions. Laboratories around the world use it. It has produced findings that are cross-referenced against other forms of evidence, including historical records, ice cores, and pollen data. The scientific community considers it reliable, and by any reasonable standard, for most of its applications, it is. But reliability is not the same as precision, and precision is where the first small doubts begin to appear. Beyond ring counting, there is another technique sometimes applied to ancient wood. Radiocarbon dating, also called carbon-14 dating, measures the decay of a specific radioactive isotope of carbon that is absorbed by all living organisms during their lifetime. When an organism dies, it stops absorbing carbon, and the carbon-14 already present begins to decay at a known rate. By measuring how much carbon-14 remains in a sample, scientists can estimate how long ago the organism died. For wood samples, this can provide an independent age estimate that either confirms or complicates the ring count. Radiocarbon dating is widely used across archaeology and geology. It has its own limitations and is most accurate within certain time ranges. For wood that is several thousand years old, it can provide useful estimates, but it relies on calibration curves, reference tables built from samples of known age that account for historical variations in atmospheric carbon levels. These curves have been refined over decades, but they are not perfectly uniform across all time periods. In some periods, a small change in the calibration assumption produces a noticeably different age estimate. That detail sounds minor at first, until it is examined more closely in the context of trees already at the edge of known biological limits. Using both of these methods together, scientists have identified trees that are over 4,000 years old. Several species have produced specimens that fall into this category, including giant sequoias, yews, and various conifers found in remote high-altitude environments. The numbers themselves are remarkable. A tree that is 4,000 years old was already ancient when the Roman Empire was founded. It was alive during the Bronze Age. It has survived through climate shifts, natural disasters, and centuries of human activity in its surrounding landscape. That survival alone raises questions that biology is still working to fully answer. The oldest confirmed living tree is a Great Basin bristlecone pine located in the White Mountains of California. Its commonly cited age is approximately 5,000 years, though the precise number has been adjusted slightly across different studies. That would place its germination roughly at the same time as or earlier than the construction of the Egyptian pyramids. It is one of the most frequently cited examples of biological longevity in the natural world. The tree is real. Its age has been examined by multiple researchers, and yet, even here, the details of how that age was confirmed are worth understanding more carefully. The scientific community largely agrees on these findings. Peer review, the process by which research is examined and evaluated by qualified colleagues before publication, has been applied to the major studies in this field. The findings have been cited extensively. The methods have been replicated in different locations, with broadly consistent results. This is what makes dendrochronology a credible and respected science. It is not the work of a single researcher or a single institution. It is a body of knowledge built over many decades by many independent contributors. That accumulated weight gives the conclusions a legitimacy that is difficult to dismiss. And yet, even within these accepted frameworks, there are details that don't quite line up the way they should. This is not a fringe observation. It appears in the scientific literature itself, often in the form of qualified language, phrases like, within the margin of error, or pending further analysis, or results were partially consistent. These phrases are standard in research writing. They signal that the conclusion holds, but that not everything fits perfectly. In most contexts, this is simply how science communicates nuance. But when the same kinds of qualifications appear repeatedly across multiple studies of ancient trees, they begin to form a pattern that invites closer attention. One area where this becomes visible is in the comparison of ring counts against radiocarbon results for the same specimen. When these two methods are applied to the same tree and produce closely matching numbers, it is taken as strong confirmation of the age estimate. But this does not always happen. In some cases, the numbers diverge, sometimes by decades, occasionally by more. Researchers have procedures for handling these discrepancies. They apply statistical corrections. They examine the sample for signs of contamination or unusual preservation conditions. They choose which result to weight more heavily based on established protocols. The final reported age is typically a processed and reconciled number, not a raw reading from a single measurement. That reconciliation process is sound science, but it is a process involving judgment. Different researchers applying the same protocols to the same sample can arrive at slightly different conclusions. This is known, and it is accounted for in the literature. But when the public receives an age estimate, 5,000 years, 4,800 years, that number does not carry the context of how it was produced. It arrives as a fact, and facts, presented without their surrounding uncertainty, can give a misleading impression of how settled the underlying knowledge actually is. The data has been peer-reviewed. The methods are well established. Both of these statements are true, and both of them are important. But peer review confirms that a study followed appropriate methods and reached defensible conclusions. It does not confirm that all questions have been answered, and well-established methods can still have boundaries beyond which their precision begins to diminish. For trees at the very edge of known biological age, specimens that push against or beyond what the species was previously thought capable of, those boundaries become more relevant. This is where the explanation becomes difficult, not because the science is wrong, but because the science is being asked to operate near the outer limits of what it can confidently measure. A method that works reliably for trees that are 1,000 years old may carry more uncertainty when applied to trees that are 5 times that age. The ring sequences become more complex. The wood itself may have undergone physical changes that affect how it responds to analysis. The calibration references that radiocarbon dating depends on become less certain at greater age. All of these factors are acknowledged within the field, but they are rarely part of the explanation that reaches most people. So the official story is real. The methods exist and they work. The trees are genuinely ancient. The researchers are genuinely careful. None of that is in question. What is worth holding on to, as this investigation continues, is the space between what the methods can confirm and what they are asked to confirm. That space is small in some places and larger in others. And somewhere in that space, the questions that don't yet have clean answers are still waiting. Here is where the first problem appears, and it is not a small one. It does not arrive with any announcement. It is built quietly into the very foundation of the method that most people trust without question. The study of tree rings seems straightforward when described in simple terms. 1 year, 1 ring. Count the rings, find the age. But that description, while useful as a starting point, leaves out something important, something that researchers know about, work around, and occasionally disagree on. And once this detail is understood, the confident numbers attached to ancient trees begin to feel a little less solid. Tree rings are not always as simple as 1 ring per year. That is the core of the problem. The assumption that drives the entire method, that each ring represents exactly 1 growing season, is not universally true. It is true most of the time, under normal conditions. But trees do not always experience normal conditions. They are living organisms, responding to their environment in ways that are not always predictable. And sometimes, that response produces something that looks like an annual ring, but is not. These are called false rings. The term itself is straightforward, a ring that appears to mark a year, but does not. They form when a tree experiences an interruption during its growing season, a sudden drought in the middle of summer, a brief cold snap, an outbreak of disease, or an unusual shift in temperature. The tree responds to this interruption by slowing or stopping its growth temporarily. When conditions improve, growth resumes. But the brief pause leaves a mark in the wood that, under examination, can look almost identical to the boundary between 2 annual rings. The difficulty is in the word almost. If false rings looked obviously different from real rings, identifying them would be straightforward. Researchers would simply apply a consistent visual standard and separate the genuine from the false. But that is not how it works in practice. False rings and annual rings can share many of the same physical characteristics. The density of the wood, the color transition, the width of the band, All of these features can appear similar under magnification. Distinguishing between them requires experience, careful comparison against reference samples, and in many cases, a degree of judgment that is not fully standardized across the field. This is a known issue. That phrase is important. It is not a secret. It appears in the scientific literature. Researchers who work in dendrochronology are trained to identify false rings, and the field has developed techniques for doing so. Cross-dating is one of the most commonly used. It involves comparing the ring pattern of one sample against a master chronology, a long reference sequence built from many overlapping samples. If a ring in one sample doesn't match the expected pattern from other trees in the same region during the same period, it may be flagged as a false ring. This is a reasonable approach. It has a logical basis, but it also introduces its own set of assumptions. But here is the part that doesn't fully make sense. The methods used to identify false rings are not always consistent. Different researchers examining the same sample have sometimes arrived at different conclusions about which rings are genuine and which are not. This has been documented. Studies in which multiple trained analysts examined identical samples independently have shown that their ring counts and false ring identifications do not always match. The differences are not always large, but they exist. And in a method that depends on precise counting, even small differences in ring identification can produce meaningfully different age estimates. This variability is not a sign of carelessness. It reflects a genuine challenge in the material being studied. Ancient wood, particularly from specimens that are several thousand years old, does not always present clean and easy-to-read ring sequences. The wood may have experienced compression, chemical changes, or physical distortion over centuries. The rings may be extremely narrow, making it difficult to distinguish individual boundaries. The transition between a false ring and a genuine ring may be subtle to the point where two experienced researchers, each applying reasonable judgment, reach different conclusions. Both conclusions may be defensible. Only one can be correct, and this variability introduces a margin of error that is rarely highlighted in public-facing explanations. When a tree is reported to be 5,000 years old, that number carries an implied precision. It suggests that the count was made, checked, and confirmed. It suggests certainty. But precision in the reported number does not reflect precision in the underlying measurement. The number 5,000 or 4,800, or whatever figure is attached to a given tree, is a processed result. It has been filtered through interpretation, cross-referencing, and judgment. The raw data from which it was derived carries a range of uncertainty that the final number doesn't communicate. The actual uncertainty range can be significant, especially for samples with complex or unclear ring patterns. A tree reported as 5,000 years old may, depending on how false rings are identified in its sample, have an actual age anywhere within a range of several decades on either side of that number. In some cases, the range could be wider. For most trees, this level of uncertainty doesn't change the broader conclusions very much. But for specimens at the extreme end of the age scale, those being used to establish records or anchor larger chronological frameworks, the uncertainty matters more. A difference of 50 or 100 years is not trivial when the specimen is already at the edge of what biology was thought capable of. Some trees also experience missing rings. This is the opposite problem from false rings, and in some ways it is harder to detect. A missing ring occurs when a tree's growth during a particular year is so minimal that no visible ring forms at all. This can happen during years of extreme stress, prolonged drought, severe cold, heavy insect damage, or other conditions that suppress growth almost entirely. If no ring forms, that year leaves no physical record in the wood. When a researcher counts the rings, they count one fewer than the tree's actual age. The tree appears younger than it is. This is not a theoretical concern. Missing rings have been identified in multiple species and multiple geographic regions. In some bristlecone pine samples, researchers have found evidence of missing rings after comparing the ring sequence against other trees from the same period whose growth records were better preserved. The existence of missing rings in one sample, but not another, from trees growing in similar conditions during the same years, raises its own questions about how consistently the growing environment affected different individual trees. The combination of false rings and missing rings creates a situation where errors can run in both directions simultaneously. False rings make a tree appear older than it is. Missing rings make it appear younger. In any given sample, both types of error might be present. Some may cancel each other out. Others may compound. The net effect on the final age estimate is not always predictable without extensive cross-referencing against other samples and other evidence. And that cross-referencing, while it improves accuracy, does not eliminate uncertainty. It reduces it. But reduction is not elimination, and that distinction is worth keeping in mind. So the age estimates that researchers rely on may be both older and younger than reported, depending on the sample. That is a careful way of saying something that sounds simple, but carries real weight. It means that the numbers are approximations, produced by skilled researchers using well-developed methods, but approximations nonetheless. It means that when a tree's age is stated as a single figure, that figure represents the center of a range, not a fixed point. The range exists whether or not it is communicated alongside the number, and it is rarely communicated with the same clarity as the number itself. At first, this seems like a minor technical concern, but there is a problem with treating it that way. Ancient trees are not studied only for the curiosity of knowing how old they are. Their ring sequences are used to build climate records that extend back thousands of years. Those records are referenced in broader scientific work, in studies of historical temperature patterns, in models of ecological change, in reconstructions of past environments. If the ring count contains errors, even small ones, then the climate record derived from that count also contains errors. And the further that record extends back in time, the more the errors in the foundational data matter. How confident can we really be in these numbers? That question does not have a simple answer. The researchers who study ancient trees are aware of the limitations of their methods. They work carefully to minimize error and document uncertainty where they find it. The results they produce are genuinely valuable and generally reliable within the ranges their methods can support. But the public understanding of those results often doesn't include the surrounding uncertainty. The numbers arrive already processed, already cleaned, already stated with a confidence that the raw data may not fully justify. That gap between the uncertainty that exists in the laboratory and the confidence that appears in the public explanation is where this investigation finds something worth examining more closely. It is not a gap created by dishonesty or negligence. It is a gap created by the way science communicates with a public that expects clear answers. But clear answers, in this case, may not be what the evidence actually supports. The trees are ancient. That much seems certain. But how ancient, precisely, and how reliably measured? Those questions remain more open than the confident figures suggest. And this is only the first problem. The uncertainties don't stop here. They continue, quietly, in other parts of the explanation that most people have never had reason to examine. To understand why any of this matters, it helps to step back and look at where these ancient trees are actually found. The location is not incidental. It is part of the explanation. And like much of the explanation surrounding ancient trees, it makes sense on the surface, but becomes more complicated the longer it is examined. The place, the conditions, and the history of how these trees were first studied all contain details that have not been fully resolved. And those details, taken together, raise questions that the standard account tends to move past without fully answering. The bristlecone pines of the American Southwest are perhaps the most well-documented ancient trees in the world. They have been studied more extensively than almost any other species in this context. They appear in scientific literature, in educational materials, and in public discussions about biological longevity. Their name has become almost synonymous with extreme old age in the natural world. And so, if there are problems with the official understanding of ancient trees, examining the bristlecone pine closely is a reasonable place to begin, because if the gaps exist anywhere, they are likely visible here, where the record is most detailed. These trees grow in harsh, high-altitude environments. The White Mountains of California, where many of the oldest known specimens are found, sit at elevations above 10,000 feet. The conditions there are severe by most standards. Winters are long and cold. Summers are short. Rainfall is limited. The soil is rocky, thin, and low in nutrients. Most plant species cannot survive in these conditions for long, let alone thrive across thousands of years. And yet, the bristlecone pines persist. They grow slowly, sometimes adding only a fraction of an inch in diameter over an entire century. But they continue. Scientists argue that these difficult conditions are precisely what allow the trees to live so long. The logic behind this explanation is worth understanding in some detail, because it forms the core of the official account. Stress, it turns out, can extend a tree's life by slowing its metabolism. When resources are scarce, when water is limited and the growing season is brief, a tree cannot afford to grow quickly. Its biological processes slow down. Its wood becomes extremely dense. Dense wood is harder for insects, fungi, and bacteria to penetrate. And so the very harshness that would kill most organisms becomes, for the bristlecone pine, a kind of protection. This is the explanation. And at first, it seems reasonable. The dry, cold environment at high elevation also limits the bacterial and fungal decay that would normally break down wood over time. In more temperate environments, fallen wood decomposes relatively quickly. The organisms responsible for that decomposition, various fungi, bacteria, and insects, thrive in warmer, moister conditions. At high altitude, those organisms are far less active. Wood that falls or dies in these environments can persist for thousands of years without significant decomposition. This is why researchers have found ancient dead wood from bristlecone pines that is still structurally intact after millennia. The environment, in effect, acts as a natural preservative. That part of the explanation is well supported and broadly accepted. But here is where a small doubt is worth noting. If harsh conditions are what preserve these trees, and if the White Mountains and Sierra Nevada contain large areas of similarly harsh terrain, then why are ancient specimens not distributed more evenly across that terrain? The question seems simple. The answer is less so. The mountain ranges of the American Southwest cover hundreds of square miles of high-altitude, low-moisture, rocky terrain. The conditions that researchers describe as ideal for bristlecone pine longevity are not confined to a small area. They are present across a much wider landscape. And yet the ancient specimens, the trees estimated at 3, 4, or 5,000 years old, are found only in very specific, limited zones within that landscape. This is not a detail that goes unacknowledged. Researchers are aware of it. The explanation offered is microclimate variation. This refers to small-scale differences in environmental conditions, variations in soil drainage, sun exposure, wind direction and intensity, and the way cold air settles or moves through a particular slope or valley. The argument is that these subtle differences, invisible at a large scale, create pockets of conditions that are slightly more favorable for extreme longevity. A tree on one side of a ridge experiences marginally different conditions than a tree on the other side. Over thousands of years, those marginal differences compound into significantly different survival outcomes. That explanation may be true. Microclimate variation is a real phenomenon and has been documented in many ecological contexts. But the clustering of ancient trees in such narrow zones has never been fully mapped or explained in a way that feels complete. The specific microclimatic factors that distinguish the precise locations where ancient trees survive from the nearby areas where they have not been comprehensively identified and documented. The explanation exists at a general level. The detailed evidence supporting it for these specific locations is thinner than the confidence with which the explanation is usually presented. And that gap between the general claim and the specific supporting evidence is worth noticing. There is another layer to this that becomes relevant when considering the history of how these trees were first studied. The bristlecone pines were not identified as extreme-age specimens from the beginning. Their extraordinary age was not recognized immediately. Early visitors to the White Mountains and similar high-altitude locations in the Southwest noted the trees and recorded their unusual appearance. The trees look different from most other conifers. Their wood is twisted and gnarled. Their trunks are often partially dead, with only a narrow strip of living bark remaining on an otherwise lifeless exterior. They look ancient in a visual sense, but looking ancient and being confirmed as ancient through scientific measurement are different things. Early explorers and researchers who first documented these trees in the mid-20th century noted their unusual appearance, but didn't initially suspect extreme age. Some assumed the trees were old, in the way that any obviously weathered, slow-growing tree in a harsh environment might be assumed to be old. But the specific realization that these trees might be among the oldest living organisms on Earth, that their ring counts could extend back 4,000 or 5,000 years, came later. And it came somewhat by accident, as a byproduct of research that was aimed at something else entirely. That detail sounds minor at first, but it becomes more significant when examined in context. The discovery of extreme age in bristlecone pines was not the result of a deliberate search for the world's oldest trees. It emerged from climate research, from a researcher working through ring sequences to reconstruct historical weather patterns. The age implication appeared as an unexpected finding within a different investigation. This is not unusual in science. Important discoveries often happen indirectly, but it does mean that the initial documentation of extreme age in these trees was not part of a systematic, carefully designed study of tree longevity. It was an observation made in passing that then required additional confirmation. The confirmation that followed was real and important. Other researchers examined the findings. More samples were taken. Cross-dating was applied. The conclusion that certain bristlecone pines were extraordinarily old gained support over time and through multiple lines of evidence. None of that process is being questioned here. But the conditions under which extreme age was first recognized, incidentally, during research aimed elsewhere, in the mid-20th century, using the tools and methods available at that time, are worth holding in mind, because those conditions shaped what questions were asked and what assumptions were made during the critical early period of documentation. And this is where the explanation becomes difficult in a different sense. When a field of study develops around a finding that was initially made in passing, there is a risk that the early interpretations become anchored in place before they have been fully tested. Subsequent researchers often build on the existing framework rather than starting from the beginning. The foundational measurements, the original ring counts, the first cross-dating attempts, the early age estimates, carry significant weight in the literature that follows. They are the reference points against which later findings are compared. If the foundational measurements contain uncertainties that were not fully recognized at the time, those uncertainties can persist through the subsequent literature without being clearly identified as such. This does not mean the foundational work was wrong. It means it was produced under specific conditions and with specific tools, and that the uncertainty present in that work deserves more explicit acknowledgement than it sometimes receives. The researchers who first studied the bristlecone pines did careful work by the standards available to them, but the standards have improved since then, and a full re-examination of the foundational data, using current methods, has not been uniformly applied across all the specimens that carry the most significant age claims. So the picture that emerges from looking at the location, the conditions, and the history of discovery is more layered than the summary explanation suggests. The trees grow in harsh environments, that is established. Harsh conditions contribute to their longevity. That is a reasonable inference, supported by biological logic. But the specific reasons why ancient specimens cluster where they do within those environments remain incompletely explained. The history of how their age was recognized carries its own uncertainties about early methodology, and the foundational data on which much of the current understanding rests has not been fully re-examined with modern precision. None of this leads to a clear alternative conclusion. It does not suggest that the trees are younger than reported, or that the researchers who studied them were mistaken in any fundamental way. What it suggests is that the explanation, as it is usually presented, is smoother and more complete than the underlying evidence fully supports. The rough edges, the unexplained clustering, the accidental nature of early discovery, the limitations of mid-century methodology, are real. They are part of the actual story, and they are rarely included in the version that most people encounter. That absence is itself a detail worth sitting with, because understanding what has been left out of an explanation is often the first step toward understanding what the explanation has not yet fully answered. In the 1950s, a researcher named Edmund Schulman was working quietly in the field of dendrochronology. His focus was not on finding the oldest trees in the world. That was not his goal. He was interested in climate history, in what tree rings could reveal about rainfall, temperature, and growing conditions across centuries of time that predated written weather records. Tree rings, he understood, were a kind of archive. Each one carried information about the year it formed, and by reading enough of them, across enough specimens, a researcher could begin to reconstruct what the climate of a region looked like long before any human had thought to measure it. This kind of research was important and methodical. It required patience, careful sampling, and meticulous record-keeping. Schulman traveled to remote locations across the American Southwest, taking core samples from old trees and returning with data that he would analyze back in the laboratory. His work was respected within the relatively small community of researchers who worked in this field at the time. Dendrochronology was not a widely known discipline in the 1950s. It occupied a quiet corner of scientific inquiry, important but not prominent. And so when Schulman began noticing something unusual in certain samples, the implications were not immediately obvious even to him. When he began analyzing certain bristlecone pines from the White Mountains of California, the ring counts were far higher than expected. Not slightly higher, significantly higher. The numbers suggested ages that placed these trees well beyond what any living organism had been formally confirmed to reach at that point. For a researcher focused on climate data, this was an unexpected finding. The climate record embedded in the rings was valuable, but the sheer number of rings, the age implied by their count, was something else entirely. It raised a question that Schulman could not simply set aside. Were these trees actually as old as the ring count suggested? Schulman continued his work and eventually published his findings. His key paper, which appeared in a major scientific journal in 1958, described bristlecone pines in the White Mountains as the oldest known living trees. The oldest specimen he identified, which he named Methuselah, was estimated to be nearly 5,000 years old based on his ring analysis. That number was striking. It placed this tree's origin at roughly the same period as the earliest phases of ancient Egyptian civilization. Schulman's work attracted significant attention both within and beyond the scientific community. It was one of those findings that, once stated clearly, seemed almost impossible to ignore. Schulman died later that same year, in 1958, before he could fully develop the implications of his research or respond to questions it would eventually raise. His work was taken up and extended by other researchers who recognized its importance. Over the following decades, the bristlecone pine became one of the most studied trees in the world. The identification of these trees as extreme-age specimens became a foundational element of dendrochronology and of broader scientific understanding of biological longevity. The scientific community accepted his conclusions, and they have largely remained unchanged in the decades since. But this is where some inconsistencies begin to surface. They are not inconsistencies about Schulman's honesty or his dedication to accuracy. Those qualities are not in question. The inconsistencies are about methodology, about the tools and techniques available to him at the time, and about whether the conclusions drawn from those tools have been sufficiently re-examined using the more precise instruments that exist today. Schulman's original field notes and some of his early core samples have been the subject of quiet debate among dendrochronologists. Not a loud or public debate, a quiet one, confined largely to specialized literature and professional conversation. But the debate exists. The tools available for dendrochronological analysis in the 1950s were considerably less precise than those available today. Ring examination was done largely by eye, under optical magnification that, while useful, had significant limitations. The ability to distinguish very narrow rings, to identify subtle false ring boundaries, or to detect minute physical characteristics of the wood that indicate growth anomalies, was constrained by what the technology of that period could reveal. Researchers compensated through experience and careful comparison. But experience and careful comparison, even when applied skillfully, are not the same as the high-resolution imaging, digital scanning, and chemical analysis tools that now exist. The gap between what was possible then and what is possible now is meaningful. Some re-examinations of Schulman's original data have suggested that certain ring sequences may have been interpreted differently depending on the researcher performing the analysis. This finding is significant in a quiet way. It does not say that Schulman was wrong. It says that his interpretations were not the only possible interpretations of the same physical evidence. In a method that depends on consistency and repeatability, this kind of variability is a concern. If two researchers, Each trained and careful, examine the same ring sequence and arrive at different counts or different identifications of which rings are genuine. Then the age estimate produced by that method carries more uncertainty than the single number attached to it suggests. The trees that Schulman identified still carry the age estimates he assigned, adjusted only slightly in subsequent studies. That is a notable detail. Adjusted only slightly. The foundational numbers, produced with 1950s tools by a single researcher working in the field, have remained largely stable across 7 decades of subsequent research. In some ways, this could be taken as confirmation. The numbers have held up over time because they were correct. But in another sense, it raises a different question. How thoroughly have those foundational numbers actually been tested? Have they been subjected to the kind of rigorous, technology-enabled re-examination that modern methods would allow? Or have they persisted partly because they became reference points, fixed anchors that later work was built around rather than directly challenged? This is where the explanation becomes difficult. Science generally does not start from scratch with foundational findings when there is no strong reason to doubt them. If subsequent research broadly confirms an earlier conclusion, the earlier conclusion tends to stand. This is not a flaw in the scientific process. It is how an efficient system of knowledge building works. But it does mean that foundational measurements, made under conditions that were less precise than what now exists, can remain in place for a long time without being comprehensively reevaluated. And in the case of ancient trees, where the specimens themselves are irreplaceable and where re-examination requires careful access to living or preserved material, the barriers to conducting a full modern reanalysis are real. What is worth noting is that very few of these ancient trees have been fully cored or re-examined with modern equipment. Core sampling, even when done carefully, carries some risk of damage to a specimen. For trees that are considered irreplaceable, that are, in fact, among the oldest living organisms on the planet, there are understandable reasons to limit invasive sampling. Conservation concerns are legitimate. The trees need to be protected. But this creates a situation where the primary data underlying the most significant age claims is relatively limited in volume, was collected decades ago, and has not been extensively re-verified using current technology. Most estimates for these extreme age specimens rely on a combination of original data and extrapolation, filling in what hasn't been directly measured with reasonable inferences based on what has. Extrapolation is a standard and accepted scientific practice. It is not inherently problematic, but it is worth understanding what it means in this context. When researchers extrapolate an age estimate for an ancient tree, they are combining directly measured data with assumptions about how the unmeasured portions of the tree would behave if examined. Those assumptions are based on knowledge of the species, the environment, and the ring patterns already documented. They are informed assumptions, but they are assumptions. And assumptions introduce a margin of uncertainty that exists whether or not it is explicitly stated in the final reported figure. That is not necessarily wrong. That phrase appears in careful scientific writing for a reason. It acknowledges that the method being described is imperfect without dismissing its value. Extrapolation, applied carefully, can produce reliable estimates. The question is not whether extrapolation was used, but whether the uncertainty it introduces has been fully communicated alongside the estimates it produced. In the case of Schulman's foundational work and the age estimates that followed from it, the answer to that question is not entirely clear. The estimates are presented, the methods are described, but the full range of uncertainty embedded in those estimates, including the uncertainty introduced by the technological limitations of mid-century analysis and the reliance on extrapolation for portions of the data, is not always foreground in the way that the numbers themselves are. There's also the matter of what was not preserved. Schulman's field notes, the written records of his observations, his sampling decisions, his interpretations made in real time in the field, are historical documents. Like all historical documents, they reflect the knowledge and assumptions of the person who made them at the time they were made. They do not include information that Schulman didn't know he needed to record. They do not anticipate questions that would only be asked decades later. Some of those notes have been examined by later researchers. Some of what they contain has prompted quiet questions about how certain interpretations were reached. But the notes are not a complete record, and the samples they accompanied are not all still available in their original condition. This accumulation of detail, the mid-century tools, the limited re-examination, the reliance on extrapolation, the historical nature of the foundational documents, does not amount to a refutation of Schulman's findings. It amounts to a set of unresolved questions that sit quietly beneath the confident numbers that his work produced. The trees are genuinely ancient. That conclusion is supported by enough converging evidence to take seriously. But how ancient precisely, and how reliably that precision was measured, those questions leave room that has not been fully closed. And the fact that the original numbers have remained largely stable across decades is not necessarily evidence that they have been fully confirmed. It may simply reflect that the full confirmation has not yet been carried out. That distinction is worth keeping in mind as the investigation continues. There is another layer to this that becomes more difficult to explain the longer you look at it. The questions surrounding ancient trees do not stay confined to one region or one species. They extend outward, across continents and across different scientific approaches, touching specimens that have been studied in very different ways and under very different conditions. And when you begin to examine those specimens, the ones found outside North America, in places that receive far less scientific attention, the picture becomes more complicated, not less. The uncertainty that was already present in the American bristlecone pine research becomes larger when placed alongside what is known, and what is not known, about ancient trees in the rest of the world. Ancient trees are not found only in North America. This is a straightforward fact, but its implications are worth following carefully. Claimed specimens exist in South America, Scandinavia, the island of Tasmania off the southern coast of Australia, and parts of Central Asia. Some of these trees grow in environments that share certain characteristics with the White Mountains of California: high altitude, cold temperatures, limited moisture. Others grow in conditions that look quite different. The variety of environments in which extreme age claims have been made is itself something that invites closer examination. If the explanation for bristlecone pine longevity is tied specifically to the harsh conditions of the American Southwest, then what explains similarly extreme ages reported in very different parts of the world? Some of these trees have been dated using methods similar to those applied to the bristlecone pines: ring counting, cross-dating, and in some cases radiocarbon analysis. The application of these methods to different species, in different regions, carries its own set of challenges. Master chronologies, which are essential to the cross-dating process, are most fully developed for the regions and species that have been studied longest. For trees in less studied areas, those reference chronologies may be less complete, less well-tested, and built on a smaller number of overlapping samples. This doesn't automatically make the results wrong, but it does mean that the same method, applied in a different geographic and biological context, may carry more uncertainty than it does in its most well-developed applications. Others have been estimated based on growth rate projections. This is a different approach entirely, and the distinction matters more than it might initially appear. Growth rate projection works by measuring how fast a particular species typically grows under known conditions, and then working backward from the physical size of a given specimen to estimate how long it must have taken to reach that size. If a species grows at an average rate of a certain number of millimeters per year, and a particular tree has a trunk circumference of a particular size, then a rough age estimate can be calculated from those two numbers. At first, this seems like a reasonable approach, and for a rough estimate, it can be useful. But there's a problem that becomes apparent when the method is examined more carefully. Growth rate projection assumes that a tree has grown at a consistent pace throughout its entire life, and that assumption is rarely true. Trees do not grow at a fixed rate. Their growth responds to the conditions around them. A year of abundant rainfall and mild temperatures produces faster growth. A year of drought or disease produces slower growth. Over centuries, a tree may experience dramatic swings in its growing conditions, periods of rapid expansion, followed by periods of near stagnation. If a researcher uses an average growth rate to estimate the age of a tree that spent significant portions of its life growing either faster or slower than that average, the resulting estimate will be off, sometimes by a little, sometimes by a great deal. Growth rate projection is a much less precise method than ring counting. that is acknowledged within the field, but the degree to which this limitation is communicated alongside the age estimates it produces varies considerably. Some of the trees dated using this method carry age estimates in the thousands of years, numbers that are presented in scientific publications, repeated in educational materials, and eventually absorbed into public understanding as established facts. The confidence with which those numbers are sometimes stated does not fully reflect the imprecision of the method that produced them. When researchers are pressed on this point, when the methodology is examined rather than just a conclusion, they often acknowledge the limitation, but that acknowledgement rarely makes it into the public-facing version of the claim. This creates a situation that is worth pausing on. A number is produced by a method with known and significant limitations. The number is then communicated to a wider audience without the context of those limitations. The audience receives what appears to be a fact, but the underlying process that generated that fact contained uncertainties that were never passed along with it. This pattern of confident public numbers sitting on top of less confident scientific processes is not unique to ancient trees, but it is particularly visible here, where the age claims are so extreme that the method's limitations become more consequential. The case of Old Chico illustrates this clearly. Old Chico is a Norway spruce located in the Fulufjallet Mountains of Sweden. It is frequently cited as one of the oldest trees in the world, with an age estimate of nearly 10,000 years. That number appears in articles, educational resources, and popular discussions about ancient trees. It is a striking figure. 10,000 years would place this tree's origin at the very beginning of the Holocene, the current geological epoch that followed the last major ice age. A living organism that old would be, in a very real sense, a bridge to a period of Earth's history that humans have only ever been able to study through indirect evidence. But here is where the distinction becomes important. The 10,000-year estimate does not refer to the visible trunk of Old Chico. It refers to the root system. The trunk itself is considerably younger, decades old, not millennia. Norway spruces are capable of a process called vegetative reproduction, in which the same root system repeatedly generates new trunks over time. When one trunk dies, another can grow from the same roots. The roots, in this case, are what was dated. The dating was done using radiocarbon analysis of organic material found in the root system. The result of that analysis suggested the root system had been active for approximately 10,000 years. That is a genuinely significant finding. A root system that old would represent an extraordinary degree of biological continuity. But it is not the same thing as a tree that is 10,000 years old in the way that most people understand a tree's age. When we speak of a tree's age, we generally mean the age of the living structure, the trunk, the branches, the visible organism. Old Chico's visible structure is not 10,000 years old. The age estimate applies to underground material that has been continuously regenerating new growth above it. This distinction is important, and it often gets lost in popular reporting. The way Old Chico is described in much of the coverage it receives does not clearly explain this distinction. It is presented as a 10,000-year-old tree, full stop. Readers and viewers encounter that number and form a mental image of a living organism that has stood for 10,000 years. That image is not accurate, but correcting it requires a level of detail that most popular reporting does not include. And so the impression persists, repeated and reinforced each time the story is told, gradually becoming part of a general understanding that is less precise than the science it claims to represent. This is where the gap between what the science actually shows and what gets communicated publicly becomes most visible. That gap is not created by deliberate misrepresentation. It is created by the compression that happens when complex, qualified findings are translated into simple, memorable statements. The compression removes the qualifications. What remains is a number, striking, memorable, and somewhat misleading in its apparent precision and straightforwardness. And this pattern appears not just with Old Chico, but across multiple ancient tree claims from different parts of the world. In Tasmania, ancient specimens of Huon pine have been identified, with some estimates placing their age in the thousands of years. The Huon pine grows extremely slowly, which makes it a candidate for extreme longevity. But its age estimates have also relied partly on growth rate projections, rather than comprehensive ring analysis. The species presents its own methodological challenges. and the remote location of many Tasmanian specimens means that access for thorough study is limited. Some of the numbers attached to these trees have been adjusted over time as better data became available. Others remain based on methodology that the researchers themselves describe as approximate. In parts of Central Asia and the Mediterranean, ancient olive trees and other long-lived species carry age estimates that range from several hundred to several thousand years. Some of these estimates are based on historical records, references in old documents or oral traditions that associate a particular tree with the particular historical event. Others are based on physical measurement and projection. Very few have been subjected to the kind of systematic ring analysis that the bristlecone pines received, and yet the numbers attached to them are often stated with a similar degree of confidence, cited in contexts that don't distinguish between well-supported findings and rough estimates. The gap between what the science actually shows and what gets communicated publicly is where some of the most interesting questions in this investigation live. It is not a gap that can be closed simply by pointing out that researchers know their methods have limitations. The knowledge that a limitation exists, held within the specialist community, does not automatically reach the public understanding. And once a number has been established in popular awareness, once it has been repeated often enough to feel settled, it becomes very difficult to revise, even when the underlying evidence would justify a more cautious presentation. What this layer of the investigation reveals is that the uncertainty surrounding ancient trees is not confined to the American Southwest or to any single species or method. It is distributed across multiple continents, multiple species, and multiple methodological approaches. Each case carries its own version of the same basic problem. Age estimates presented with more confidence than the underlying evidence fully supports, and a public understanding shaped more by memorable numbers than by the qualifications that originally surrounded them. The question of how old these trees actually are, and how reliably that age has been determined, does not become simpler as the investigation broadens. It becomes more complicated, and that complication is itself something worth sitting with. A pattern begins to emerge when you look across different ancient tree claims from different parts of the world. It is not an obvious pattern. It does not announce itself. It becomes visible only when you step back from individual cases and look at how the record as a whole has developed over time. And once it becomes visible, it is difficult to look past. The pattern is not about any single tree or any single study. It is about the behavior of the age estimates themselves, how they change, how often they change, and how quietly those changes tend to happen. Age estimates for ancient trees are frequently revised, sometimes significantly, and often without much public notice. A tree that was reported as 3,000 years old in one decade appears in later records as 4,000 years old. Another tree that once held a prominent position on lists of the world's oldest known specimens is quietly removed from those lists without a clear public explanation. A number that felt settled turns out to have been provisional, and the revision, when it comes, arrives without the same attention that the original claim received. This asymmetry, where initial findings travel widely and corrections travel quietly, shapes public understanding in ways that are easy to overlook. This pattern is not unique to the study of ancient trees. Science updates itself. That is part of how it works, and it is generally a sign of a healthy and functioning process. When new data becomes available, when better tools allow a more precise measurement, or when a re-examination of existing evidence reveals an earlier error, the responsible course is to revise the record. Most fields of science do exactly this. The question is not whether revision happens. The question is what the frequency and nature of these particular revisions can tell us about the underlying reliability of the estimates being revised. In most well-established fields, major revisions to foundational findings are relatively infrequent. When they do occur, they are typically accompanied by detailed explanation, a published correction, a new study that clearly identifies what changed and why, a public acknowledgement of what the earlier estimate got wrong. This is how scientific accountability is supposed to work. The revision is not hidden. It is documented, and that documentation allows other researchers, and the broader public, to understand not just that something changed, but why it changed and what the new estimate is based on. But in the record of ancient tree age estimates, The revisions do not always follow this pattern. Some changes appear in updated databases or revised lists without a corresponding publication that explains the change in detail. A number shifts. A tree moves up or down in the rankings. A specimen disappears from the record entirely. These changes are not secret. They can be found by anyone who looks carefully enough. But they are not prominently communicated. They do not receive the same coverage as the original claims. And so the public record of which trees are oldest and how old they are contains a quiet instability that most people who encounter it have no way of detecting. In some cases, trees that were once featured prominently in scientific literature have been re-examined and found to be considerably younger than originally reported. These are not minor adjustments. In some instances, a tree's estimated age has been reduced by centuries after more careful analysis. The original estimate was made in good faith, using the methods available at the time. The re-examination, using better tools or more extensive sampling, produced a different result. But the earlier number, having already circulated in the literature and in public awareness, doesn't simply disappear. It lingers in older sources, in educational materials that haven't been updated, in reference works that repeat what was established without noting what was subsequently revised. In other cases, trees overlooked for decades have been identified as significantly older than any previously known specimen. This is perhaps the more striking direction of revision. A tree growing in a known location, in a region that has been studied for years, turns out to have been dramatically underestimated in age. The oversight is not the result of negligence. It reflects the practical reality that not every tree in a given area can be thoroughly sampled and analyzed. Researchers work with limited time and resources. They make decisions about which specimens to prioritize. And sometimes, a tree of extraordinary age sits unexamined for decades, simply because no one had yet gotten to it. The case of the bristlecone pine, known as Prometheus, makes this concrete in a way that is difficult to set aside. Prometheus was a tree growing in the Snake Range of Nevada. In 1964, a graduate student conducting research in the area used a coring tool on the tree, and, when the tool became stuck, received permission from the local Forest Service to cut the tree down in order to retrieve it. The permission was granted. The tree was cut. Only afterward, when the cross-section was examined, did researchers realize what had been lost. The ring count from the stump of Prometheus produced an age estimate that exceeded 4,900 years. By some analyses, it may have been older than Methuselah, the bristlecone pine in California that Schulman had identified as the oldest known living tree. If those estimates are accurate, Prometheus was not merely ancient. It was potentially the oldest individual tree organism ever documented, and it was gone before anyone had formally recognized what it was. Why wasn't its age recognized before it was cut? The answer given by the scientific community is straightforward. The tree had not been formally sampled before the incident. No researcher had taken a core from it and counted its rings. It had not been flagged as a priority specimen. In a landscape containing many old trees, this particular one had not yet received the specific attention that would have revealed its age. That explanation is factually accurate, but it raises a question that is harder to dismiss with a straightforward answer. If a tree of nearly 5,000 years, potentially the oldest individual tree ever recorded, could exist in a studied region, in a species that was already the focus of active age research, without anyone having formally measured it before it was destroyed, then the inventory of ancient trees is far less complete than it might appear. The White Mountains had received significant research attention by 1964. Schulman had been working there for years. Other researchers had followed, and yet Prometheus, in a different range of the same general region, had not been examined. Its age was unknown, and once it was cut, it became a data point and a record of loss, rather than a living specimen that could continue to be studied. This raises a broader question that the existing record cannot fully answer. How many other trees of similar or greater age exist unrecognized? How many are growing in locations that have not yet received systematic research attention? How many are in areas that are difficult to access, remote slopes, protected wilderness, regions where the relevant species has not been prioritized for study? And how many have already been lost to logging, to fire, to disease, or simply to the passage of time, before their age was ever measured? These questions do not have answers. That is precisely what makes them significant. The record of the world's oldest trees is not a complete inventory. It is a record of what has been found and measured among the trees that researchers happen to examine. The difference between those two things, a complete inventory and a record of examined specimens, is potentially very large, and the case of Prometheus demonstrates that the gap between known and unknown can contain specimens of extraordinary significance. The frequency of revisions in this record, combined with the case of Prometheus and the broader issue of incomplete sampling, points towards something that deserves more explicit acknowledgement than it usually receives. The list of the world's oldest trees is not stable. It is not settled. It is a working document, subject to change as new specimens are examined and old estimates are revisited. Some believe the list is reasonably accurate as a general guide to the upper range of tree longevity. Others point to cases like Prometheus to argue that the upper range itself may not yet have been found. Neither position can be confirmed with the data currently available, and this is where the explanation becomes difficult in a way that goes beyond technical methodology. The incompleteness of the record is not just a scientific problem. It is also a communication problem. When lists of the world's oldest trees are presented to a general audience, they carry an implied completeness that the underlying research process does not support. They look like rankings. Rankings imply that all the candidates have been assessed and placed in order. But in this case, many candidates have never been assessed. Some that were assessed with imprecise tools, and some that might have ranked at the very top were lost before they could be assessed at all. The pattern of revision without prominent explanation, the existence of significant specimens that went unstudied for decades, and the loss of potentially record-breaking trees before their significance was recognized all point toward the same underlying issue. The confidence with which the record of ancient trees is presented does not match the incompleteness and instability of the record itself. That mismatch is not created by bad intentions. It is created by the natural tendency to present findings in a form that emphasizes what is known rather than what remains unknown. But in this investigation, what remains unknown is not a minor footnote. It is, in some ways, the most important part of the story. How many trees of similar or greater age already exist unrecognized, unstudied, or already lost? That question was left open by the case of Prometheus 60 years ago. It has not been closed since. The research has continued, and more specimens have been identified and measured, but the fundamental incompleteness of the inventory has not been resolved. New ancient trees are still being discovered, estimates are still being revised, and the pattern of quiet change in a record that is publicly presented as settled continues, with each revision quietly confirming that what seemed certain was, in fact, still being worked out. The problem expands when you begin to consider what ancient trees actually represent beyond their age. Age alone would make them remarkable, but age is not the only reason they matter to science. These organisms were alive during periods that human beings know very little about. They existed before written records. They existed before most of the historical evidence that archaeologists and historians rely on, and inside their wood, they carry something that written records cannot provide. A continuous, year-by-year account of the environmental conditions they experienced across thousands of years. That account is what makes ancient trees significant far beyond the question of how old they are. The rings inside an ancient tree are not just a calendar. They are a record. Each ring contains information about the year it formed, information about temperature, about rainfall, about the length of the growing season, about the presence or absence of stress events like drought or cold snaps. When researchers measure the width of each ring and analyze the density and chemical composition of the wood within it, they can extract a detailed picture of what the climate looked like during that particular year. Over a tree with thousands of rings, this produces a climate record of extraordinary length, one that reaches back into periods of history that no human instrument ever measured. This kind of data is called a proxy climate record. The word proxy is important here. It means that the data is not a direct measurement of past climate. It is an indirect record, a biological response to climate conditions, preserved in organic material. Tree rings are one of the most widely used proxy records in climate science. They are considered valuable because they are annual. meaning each data point corresponds to a specific year rather than a broad period. Other proxy records, ice cores, ocean sediments, pollen deposits, often have lower temporal resolution. Tree rings, in theory, offer the kind of year-by-year precision that other archives cannot. Researchers have used this tree ring data to reconstruct temperature and rainfall patterns far beyond the reach of written history. These reconstructions extend back thousands of years. They describe what conditions were like during periods that no human recorded. They identify warm periods and cold periods, drought cycles and wet periods, events that affected agriculture, migration, and the rise and fall of ancient societies. The reconstructions are not simple or uniform. They are built from large datasets, combining ring records from many trees across many regions, processed through statistical methods designed to separate the climate signal from other sources of variation. The result is a historical climate record that scientists use as a reference point for understanding how the Earth's climate has behaved over long periods of time. These reconstructions influence scientific models of climate change. This is where the significance of tree ring data extends well beyond the study of trees themselves. Climate models, the computational tools used to understand how the Earth's climate system works and how it may change in the future, are built on assumptions about how the climate has behaved in the past. Proxy records, including tree ring data, are part of the evidence base that informs those assumptions. If the proxy record suggests that the Earth's climate was relatively stable over a certain period, that influences how the model is calibrated. If it suggests that temperatures fluctuated significantly within a certain range, that influences the model differently. The tree ring record, in other words, is not just historical data. It is an input into tools that shape current scientific understanding and policy discussion. But this is where it becomes unclear. If the ring counts that form the foundation of this data contain errors, if false rings have been miscounted, if missing rings have gone undetected, if the age estimates assigned to individual specimens carry more uncertainty than has been communicated, then the climate reconstructions built on top of that data also carry those errors. This is not a theoretical concern invented by critics of climate science. It is a concern that has been raised within the dendrochronological community itself, in technical literature, by researchers who understand the method's capabilities and its limitations. The concern is real, it is documented, and it deserves more attention than it typically receives in contexts where the reconstructions are being used and cited. Some researchers have noted that different tree ring datasets from the same geographic region do not always agree with each other. This is a significant observation. If two datasets, each built from tree ring samples collected in the same region and covering the same time period, produce different climate signals, then at least one of them contains error, or both do. The disagreement indicates that something in the data, or in the process of building the dataset, has introduced inconsistency. In a well-functioning measurement system, independent measurements of the same phenomenon should converge on the same result. When they diverge, the divergence itself becomes evidence of a problem that needs to be identified and addressed. When datasets conflict, there are methods for reconciling them. This is acknowledged openly in the field. Statistical techniques exist for combining conflicting datasets, for identifying outliers, for weighting different records based on their assessed reliability. These techniques are sophisticated and are applied by researchers who understand their purpose and their limitations. But they involve judgment calls, deciding which dataset to weight more heavily, which data points to exclude as anomalies, and how to handle periods where the records diverge most significantly are not purely mechanical decisions. They require interpretation, and interpretation, even when guided by clear principles, introduces variability that is not always transparent in the final product. That lack of transparency is part of what makes this difficult to evaluate from the outside. The final reconstructed climate record looks authoritative. It is presented as a coherent history of past conditions, supported by extensive data and rigorous analysis. But the process that produced it involved decisions about which samples to include, how to handle conflicting data, how to apply statistical corrections, that are documented in technical publications but rarely visible in the public presentation of the results. Someone encountering the reconstruction without access to the methodological details has no way of knowing which parts of the record rest on strong consistent data, and which parts rest on reconciled, adjusted, or interpolated estimates. However, the timeline does not fully match in certain places that researchers themselves have identified. Some periods within the long tree ring record show higher disagreement between datasets than others. Some species show stronger and more consistent climate signals than others. Some geographic regions are better represented in the overall dataset than others. These variations in data quality are known. They are accounted for, to the extent possible, in the statistical processing. But accounting for uneven data quality is not the same as having uniform, high-quality data throughout. The reconstruction that emerges from this process is not equally reliable across all the time periods it covers. Some parts are better supported than others, but that variation is rarely visible in the way the reconstruction is typically presented. The implications stretch further than the trees themselves. This is perhaps the most important point in this part of the investigation. The uncertainty embedded in tree ring data does not stay contained within the study of ancient trees. It travels outward, into the climate models that reference the reconstructed record, into the archaeological interpretations that use climate data to understand historical societies, into the ecological baselines that researchers use to assess how environments have changed over time. Each of these fields draws on the tree ring record as a source of information about the past, and each of them inherits, to some degree, the uncertainties that are built into that record. Archaeological interpretation is one area where this connection is worth examining. Researchers studying ancient civilizations often draw on climate reconstructions to understand the environmental context in which those societies developed and declined. A drought reconstructed from tree ring data might be offered as a contributing explanation for the collapse of a particular culture at a particular time. A period of favorable climate might be used to explain a period of expansion or agricultural prosperity. These connections are often presented as established explanations, but if the climate reconstruction that underlies them contains errors or uncertainties in the relevant time period, then the explanation built on top of it becomes correspondingly uncertain. The history, in that case, is only as reliable as the proxy record it was built from. If the biological record is uncertain, then parts of the historical and climate record built on top of it may also be less settled than commonly presented. That statement does not claim that the record is wrong. It claims that the record carries inherited uncertainty, uncertainty that originated in the biological data and has been passed forward into the interpretive frameworks built from it. This kind of inherited uncertainty is difficult to trace once it has been absorbed into a larger body of knowledge. The tree ring data becomes climate reconstruction. The climate reconstruction becomes historical context. The historical context becomes accepted explanation. At each step, the original uncertainty becomes less visible. This doesn't mean the record is wrong. That distinction is important to maintain. The research that produced these records is real, careful, and conducted by people with genuine expertise. The climate reconstructions that draw on tree ring data have produced findings that are broadly consistent with other forms of evidence, including ice core records and historical documents where those exist. Consistency across multiple independent lines of evidence is a meaningful form of validation. It doesn't guarantee accuracy in every detail, but provides a basis for reasonable confidence in the general picture. What it does mean is that the uncertainty is larger than the confidence of the public-facing number suggests, and that gap between the stated certainty of the reconstructed record and the actual uncertainty present in the data that produced it is difficult to fully explain in a short summary. It exists not because anyone has hidden it, but because the process of translating complex, qualified scientific findings into accessible public communication consistently loses some of the nuance. The qualifications that researchers include in their technical publications do not survive the translation intact. What arrives at the public level is a cleaner, more certain-sounding version of findings that, in their original form, carried considerably more hedging. That gap between stated certainty and actual uncertainty is where this part of the investigation finds its most important unresolved question. Not whether the trees are old, not whether tree ring data is useful. Both of those things appear to be true. The question is whether the way that data is being used, and the confidence with which the results are being presented, accurately reflects what the underlying evidence actually supports. And based on what the record shows, the conflicting datasets, the judgment calls and reconciliation, the inherited uncertainty carried forward into historical and climate interpretation, that question does not yet have a satisfying answer. Several alternative interpretations have emerged over time from researchers, independent scientists, and historians who have approached these questions from angles that differ from the mainstream. These interpretations are not widely accepted. They have not displaced the standard explanations that dominate scientific literature and educational materials. But they exist. They have been put forward by people who have examined the same evidence and reached different conclusions, or who have identified aspects of the evidence that they believe the mainstream account has not fully addressed. And in an investigation that has already uncovered significant uncertainty within the accepted framework, these alternative views deserve at least a careful and fair examination. It is worth being clear about what acknowledging these views does and does not mean. It does not mean they are correct. It does not mean that the mainstream scientific consensus on ancient trees is wrong. What it means is that the questions surrounding ancient trees have attracted serious attention from people who looked carefully and found the standard answers incomplete. Some of those people hold academic positions. Others work independently. Some come from adjacent fields, geology, archaeology, atmospheric science, and bring perspectives that pure dendrochronologists may not have prioritized. Their conclusions vary. Their methods and reasoning vary. But the thread connecting them is a shared sense that the official explanation, while largely sound, leaves certain details unaddressed in ways that matter. Some researchers suggest that certain ancient tree populations may have survived from periods far earlier than current models predict. This is perhaps one of the more striking alternative claims, and it requires some unpacking to understand what it actually proposes. Current models of paleoclimate, the study of past climate conditions, describe the environmental history of various regions in terms of what conditions prevailed at different periods. These models are built from multiple sources of evidence, including tree ring data, ice cores, pollen records, and geological analysis. They describe when certain regions were warm or cold, wet or dry, forested or open, and they make predictions about what environmental conditions would have allowed or prevented the survival of particular organisms across long time periods. The alternative view being raised here suggests that some ancient tree populations may have persisted through periods that current models describe as inhospitable to their survival. The implication is that either the trees survived conditions more extreme than they are known to tolerate, or that the conditions in those specific locations were different from what the regional models predict, or that the models themselves are less accurate for certain periods than they are assumed to be. Researchers who hold this viewpoint to the unusual soil chemistry found around some ancient groves as part of their evidence. The soil in these locations, they argue, contains chemical signatures that suggest environmental conditions very different from those present in surrounding areas today. Conditions that, in some cases, do not match what current models would predict for that region across the relevant time periods. Soil chemistry is a legitimate area of scientific study. The chemical composition of soil reflects the history of what grew in it, what decomposed in it, and what environmental processes acted on it over time. Unusual chemistry in the soil around ancient groves is a real observation, not an invented one. But what that unusual chemistry means, whether it reflects survival from much earlier periods, or simply the long-term influence of the trees themselves on their immediate environment, or some other localized geological process, is not settled. The observation is noted. The interpretation remains open, and that openness is itself something worth sitting with, because the mainstream explanation for why these trees survive where they do does not always account for the soil chemistry detail in a fully satisfying way. Others have suggested that some reported ancient trees may be younger organisms growing from root systems of far older parent trees. This view draws directly on the old Chico situation examined earlier, but extends it more broadly. The argument is that the distinction between an individual organism and a clonal colony, between a single tree and a group of genetically identical stems produced by the same root system, has not always been made clearly in the literature on ancient trees. If a root system generates a new trunk every few centuries, The visible tree at any given moment may be relatively young even if the underlying biological entity is extremely old. Age estimates based on the visible trunk would then dramatically understate the age of the root system, while age estimates based on the root system would not accurately describe the age of the visible organism. This distinction matters for more than just record keeping. It affects what we mean when we say a tree is ancient. It affects how we interpret the biological evidence these trees contain. If the trunk being cored and analyzed is a few hundred years old rather than a few thousand, the climate data embedded in its rings covers only the period of that trunk's growth, not the full history of the root system beneath it. Some believe the field has not always been sufficiently careful about making this distinction explicit, and that some age claims in the literature conflate the age of the root system with the age of the individual stem in ways that are not clearly flagged. Others disagree, arguing that researchers in this field are well aware of the distinction and apply it carefully. The disagreement exists, and the fact that it exists, even quietly, is worth acknowledging. A smaller group of independent researchers raises a more technically focused concern. They question the reliability of the radiocarbon calibration curves that are used when carbon dating is applied to wood samples. To understand this concern, it helps to recall how radiocarbon dating works. Carbon-14, the radioactive isotope used in dating, is absorbed by living organisms from the atmosphere. The concentration of carbon-14 in the atmosphere has not been constant over time. It has varied due to changes in solar activity, geomagnetic field strength, and other factors. Because the atmospheric concentration varies, a simple measurement of how much carbon-14 remains in a sample is not sufficient to determine its age. The measurement must be compared against a calibration curve, a reference record that maps known carbon-14 concentrations in the atmosphere to specific time periods. These calibration curves have been built over decades using samples of known age, tree rings from ancient wood, coral records, cave deposits, and other materials whose age can be independently verified. The curves are regularly updated as new data becomes available. They are considered reliable across most of the time range relevant to ancient trees. But this smaller group of researchers argues that certain historical periods may have involved atmospheric conditions that are not fully captured in the current calibration curves, conditions that would make carbon dating less precise for samples from those eras. If the calibration reference for a particular period is less accurate than assumed, then age estimates derived from radiocarbon dating of samples from that period would also be less accurate, in ways that might not be apparent from the stated margin of error. This concern is not widely accepted in mainstream science. Most researchers in the field point to the ongoing refinement of calibration curves and to the broad consistency between radiocarbon results and other independent dating methods as evidence that the curves are reliable. And for most purposes and most time periods, that consistency does provide a meaningful basis for confidence. But the researchers raising this concern are not disputing the general reliability of radiocarbon dating. They are raising a more specific question about precision at particular time periods, the very periods that are most relevant to the oldest ancient tree specimens. That detail sounds minor at first, until it is examined in the context of trees, whose age claims rest partly on radiocarbon results from those specific periods. None of these alternative views have gained significant traction within established science. This is an important fact to state clearly. The scientific community has not adopted these interpretations. They have not replaced or substantially modified the mainstream understanding of ancient trees. Most researchers who work in dendrochronology and related fields are aware that alternative views exist and have considered them, at least in general terms. Their conclusion, for the most part, is that the alternative explanations are less well supported than the mainstream account, and that the anomalies they point to can be explained within the existing framework without requiring a fundamental revision of the accepted understanding. Most mainstream researchers point to the consistency of results across multiple methods as their primary form of validation. This is a significant argument. When ring counting produces an age estimate that broadly agrees with radiocarbon dating, and when both of those broadly agree with comparative data from other trees and other proxy records from the same region and period, that convergence provides a meaningful basis for confidence. Independent methods, with different sources of potential error producing similar results, is exactly what a reliable measurement system should look like. The consistency argument is not merely rhetorical. It reflects a genuine and important feature of how the evidence has developed. But consistency across methods is only as reliable as the methods themselves. And this is where the alternative researchers find their most defensible ground. If two methods share a common assumption, if both ring counting and radiocarbon dating are calibrated against reference materials that carry the same unexamined uncertainty, then their agreement with each other does not fully validate either one. Consistency between methods can reflect genuine accuracy, but it can also reflect shared assumptions that have not been independently tested. Distinguishing between these two possibilities requires exactly the kind of detailed examination of foundational assumptions that the alternative researchers are calling for, and that examination has not been fully carried out for the oldest specimens. Some believe those methods, while generally sound, carry assumptions that haven't been fully tested against the oldest specimens specifically. The general soundness of dendrochronology and radiocarbon dating is well established for a wide range of applications. The concern being raised is not about the methods in general. It is about whether those methods have been rigorously validated at the extreme end of the age range, the 5,000-year, the 10,000-year claims, where the biological and atmospheric conditions being modeled are furthest from the conditions under which the methods were initially developed and tested. This is a narrower and more specific concern than a general critique of the methods, and it is one that has not been definitively answered. What is true is that the disagreement exists, even if quietly. It does not appear in headlines. It does not dominate the scientific conversation about ancient trees, but it is present in the literature, in conference discussions, in the careful language of technical papers that acknowledge limitations without fully resolving them. The researchers raising alternative views are working at the edges of an accepted framework, pointing toward details that the framework has not yet fully integrated. They may be wrong. The mainstream account may be essentially correct in all its important features, but the history of science contains enough examples of quiet, persistent minority views eventually revealing something important to make a thoughtful investigator hesitant to dismiss them entirely without understanding what exactly is driving them. The disagreement, quiet as it is, reflects something real. It reflects the fact that the evidence surrounding ancient trees contains unresolved details that different researchers, approaching the same material with different assumptions and different areas of focus, interpret differently. The mainstream handles these details one way. The alternatives handle them another way. Neither side has access to evidence complete enough to fully settle the question, and until the foundational data has been more comprehensively re-examined and the oldest specimens more thoroughly studied with current technology, the disagreement is unlikely to fully resolve. It will remain quiet, present, and worth keeping in mind as the investigation reaches its final consideration. After looking at all of this carefully, what becomes clear is not what most people might expect. The conclusion of this investigation is not that the official explanation is fabricated, or that the science surrounding ancient trees is built on deliberate misrepresentation. That is not what the evidence shows. What the evidence shows is something quieter and, in some ways, more difficult to resolve. The official explanation is real. The methods are real. The trees are genuinely extraordinary. But the explanation is less complete than it appears. And that gap between appearance and reality, between the confident version that reaches the public and the more uncertain version that exists within the research itself, is what this entire investigation has been tracing. The methods used to date ancient trees are real, tested, and broadly reliable. That statement deserves to be taken seriously. Dendrochronology has been developed over more than a century. It has been applied by thousands of researchers across dozens of countries and hundreds of species. It has produced findings that have been cross-referenced against independent lines of evidence and found to be broadly consistent. Radiocarbon dating has a similarly extensive track record. These are not fragile or untested tools. They are genuinely useful scientific instruments that have contributed enormously to human understanding of biological history, climate history, and the deep past. None of the questions raised in this investigation are meant to suggest otherwise, but they contain known limitations, that are rarely communicated alongside the confident numbers given to the public. This is the persistent gap that this investigation has returned to repeatedly, from different angles and through different examples. The limitations are real. They are documented within the scientific community. False rings exist and are not always consistently identified. Missing rings exist and can make trees appear younger than they are. Growth rate projections carry significant uncertainty that is not always visible in the estimates they produce. Foundational measurements made with mid-century tools have not been comprehensively re-examined with modern technology. Radiocarbon calibration curves carry their own uncertainties at specific time periods. Each of these limitations is known. Each of them is acknowledged somewhere in the technical literature, but none of them travel reliably alongside the age estimates when those estimates reach a general audience. The trees themselves are extraordinary. That much is genuinely not in question. When you consider what it means for a living organism to have persisted for 4, 5, or even 10,000 years, through ice ages, droughts, wildfires, and centuries of human activity in surrounding landscapes, the word extraordinary feels almost insufficient. These specimens represent something that biology struggles to fully explain. Their survival over such timescales, under conditions that would have killed most organisms many times over, places them in a category that science has only recently begun to study with the seriousness it deserves. And that unusualness, the sheer improbability of their existence, has made them objects of both scientific study and public fascination for decades. But some details don't fully match the explanation that has been built around them. And this is the part that the investigation keeps returning to. Not because the mismatches are dramatic, but because they are persistent. They appear across different specimens, different regions, different methodological approaches, and different periods of research. They do not all point in the same direction. They do not all suggest the same kind of error or the same kind of alternative explanation. But their persistence, the fact that they keep appearing in different forms across different parts of the record, is itself a form of evidence. Evidence not of any specific alternative conclusion, but of the incompleteness of the current one. The clustering of ancient specimens in narrow geographic zones remains unexplained in a fully satisfying way. This detail was raised early in the investigation and has not been resolved since. The explanation offered, microclimate variation, small differences in local conditions that create pockets of favorable survival, is plausible in general terms. But the specific factors that distinguish the precise locations where ancient trees survive from the nearby areas where they do not have not been comprehensively mapped or documented. The explanation exists at the level of general principle. The detailed evidence that would confirm it for specific locations is thinner. And this matters because the location of ancient trees is not a minor detail. It is central to understanding why they survive where they do, which is, in turn, central to understanding what they can tell us. The revision history of age estimates follows a quiet but notable pattern. This too was examined in detail and has not resolved into a comfortable conclusion. Estimates change. Trees move up and down in the rankings of oldest known specimens. Numbers that were presented as settled turn out to have been provisional, and these changes happen without the prominence that the original claims received. The asymmetry between how confidently initial findings are communicated and how quietly revisions are absorbed into the record is not unique to this field, but it is particularly visible here, where the original numbers carried such weight and where the revisions touch findings that are foundational to larger scientific frameworks. The gap between root system age and trunk age is frequently lost in popular communication. The old Chico example illustrated this clearly. A 10,000-year-old root system is not the same biological entity as a 10,000-year-old tree, in the way that most people understand a tree. The distinction is real and scientifically important, but it is routinely absent from the popular presentations of these findings. The number travels, the qualification does not, and the public understanding that forms around the number is therefore less accurate than it could be. Not because anyone deliberately created a false impression, but because the process of simplifying complex findings for wide communication consistently leaves important nuance behind. The climate data built on tree rings carries uncertainties that ripple outward in ways that are difficult to fully trace. This was perhaps the most significant expansion of the original question, the point at which the investigation moved beyond the trees themselves and into the broader frameworks that depend on them. When tree ring data is used to build proxy climate records, and those records are used to calibrate climate models, and those models are used to interpret historical events and project future conditions, the uncertainties embedded in the original data are inherited by everything built on top of it. That inheritance is real. It is not always visible, and it has not been fully accounted for in the way climate reconstructions are typically presented and used. None of these points resolve into a single clear answer. That is an honest assessment, not an evasion. If the evidence pointed clearly toward a specific alternative explanation, if there were a definitive case that the age estimates are systematically wrong by a particular margin, or that the climate reconstructions contain a specific identifiable error, that would be a different kind of investigation, and it would have a different kind of conclusion. But the evidence does not do that. What it does is accumulate. Each individual point of uncertainty might be dismissed on its own as a technical detail within an otherwise solid framework. But when these points are assembled together, the false rings, the missing rings, the growth rate projections, the foundational mid-century measurements, the revision pattern, the geographic clustering, the root system confusion, the dataset disagreements, they form something larger than a collection of minor technical concerns. The researchers working in this field are serious people doing careful work. This too deserves to be stated clearly and meant sincerely. The men and women who have devoted their careers to studying ancient trees, to developing and refining dendrochronology, to building climate reconstructions from biological proxy data, they are not careless. They are not incurious about the limitations of their methods. The technical literature shows that they are aware of the concerns raised in this investigation. They write about false rings and missing rings. They acknowledge dataset disagreements. They discuss the challenges of foundational measurements and the limitations of calibration curves. The knowledge of these limitations exists within the field. What the investigation has traced is the gap between where that knowledge lives and where it ends up when findings are communicated to the wider world. But the picture they have assembled is still incomplete in ways that have not been openly acknowledged in the places where most people encounter this subject. An incomplete picture is not the same as a wrong picture. Incompleteness means that there are parts of the image that have not yet been filled in, areas where the evidence does not yet reach, where the questions have not yet been answered, where the methods have not yet been fully applied to the specimens that would most benefit from them. The incompleteness is real. The researchers themselves would likely agree with that characterization in their more candid moments. What is less clear is whether that incompleteness is communicated with the same regularity and prominence as the parts of the picture that are filled in. These trees have stood for thousands of years, through changes in climate that altered the landscapes around them, through the rise and fall of civilizations that had no knowledge of their existence, through centuries of human activity that brought explorers, scientists, and eventually tourists to their vicinity. They have endured in a way that almost nothing else on Earth has endured, and they have done so while quietly accumulating a record of everything they experienced, a record written in wood, in rings, in the chemistry of ancient cells that formed under conditions no human ever directly observed. That record is extraordinary, and the fact that humans have developed methods capable of reading parts of it is itself a significant achievement. They contain a record that humans are still learning to read. That sentence carries more weight than it might initially appear to. Still learning suggests that the reading is not complete, that the methods currently applied to these records are not the final word on what those records contain, that future technology, future analysis, future questions not yet asked might reveal things about these trees that current understanding has not yet captured. This is almost certainly true. Science in any active field is always still learning, but in the case of ancient trees, the gap between what has been read and what remains unread seems larger than the current public understanding of these trees would suggest. And perhaps the most honest thing that can be said, after following this investigation through all of its layers, is this: we do not yet fully know what that record says. Not in the sense of knowing nothing. The research has produced genuine and valuable findings, but not in the sense of having reached a settled, complete, and fully verified understanding either. The age estimates are real, but carry more uncertainty than the numbers suggest. The climate data is valuable, but rests on foundations that have not been uniformly re-examined. The explanations for where these trees grow and why they survive are plausible but incomplete. The alternative views are unproven, but point toward genuine gaps that the mainstream account has not fully closed. What remains, at the end of this careful look, is not a refutation and not a confirmation. It is an open question, or rather, a collection of open questions that sit quietly beneath a confident public narrative. The trees are still there, growing slowly in their narrow zones at high altitude, adding rings that future researchers will eventually examine with tools that do not yet exist. Whatever those future examinations reveal, they will likely add something to the picture that is currently missing. And that possibility, that the picture is genuinely still being assembled, may be the most important thing this investigation has found. 4:41 a.m. After everything that has been examined, after every detail that has been turned over and looked at from different angles, something still remains. It is not a conclusion. It is not a final answer. It is more like a feeling that the investigation has reached the edge of what the current evidence can clearly show, and that beyond that edge, there's more territory that has not yet been fully explored. That feeling is not comfortable, but it is honest. And in an investigation like this one, honesty about what is not known matters at least as much as clarity about what is. The questions that opened this investigation have not been closed. They have been examined more carefully, placed in broader context, and connected to larger frameworks. But they remain open. The age estimates attached to ancient trees still carry uncertainties that the public numbers do not communicate. The methods used to produce those estimates still contain known limitations that are rarely foregrounded when the results are presented. The climate data built on tree ring records still inherits the uncertainties present in its foundational material, and the explanations offered for where ancient trees grow, how they survive, and what they represent still leave details unaddressed that a complete account would need to resolve. But this is where something important becomes visible. The openness of these questions is not simply a problem to be solved. It is also information. When questions in a well-studied field remain open after decades of serious research, that persistence tells us something. It tells us that the subject is more complex than the simplified version suggests. It tells us that the evidence, taken carefully and honestly, does not fully support the level of certainty that public-facing accounts tend to project. And it tells us that the distance between what is known and what is assumed to be known is larger than most people who encounter this subject have been given reason to suspect. That distance is not unique to the study of ancient trees. It appears in many areas where complex scientific findings are translated into public understanding. The translation process compresses nuance. It removes qualifications. It replaces ranges with single numbers and replaces uncertainty with confidence, because confidence is easier to communicate and easier to absorb. The result is a public understanding that is broadly shaped by the real science, but that consistently overstates how settled that science actually is. In most cases, this compression does limited harm. But in cases where the foundational data is being used to support larger frameworks, climate models, historical reconstructions, ecological baselines, the compression carries more consequence than it might appear to. Ancient trees sit at exactly that kind of junction. They are not just biological curiosities. They are data sources. Their rings feed into records that feed into models that feed into interpretations of both the deep past and the near future. The uncertainty embedded in those rings does not stay contained within the narrow question of how old a particular tree is. It travels outward, quietly, into frameworks that depend on the tree ring record being as precise and reliable as it is assumed to be, and the degree to which that assumption has been fully tested, particularly at the extreme end of the age range, where the most significant claims are made, is a question that this investigation has found difficult to answer with confidence. There is also something worth considering about what has not been studied. The inventory of ancient trees around the world is incomplete. This was established clearly through the case of Prometheus, a tree of extraordinary age that existed in a studied region, in a studied species, and was destroyed before its significance was recognized. If that could happen in the White Mountains of California, in the middle of active dendrochronological research, then the possibility that comparable or greater specimens exist unexamined elsewhere is not a remote one. It is a realistic one. The world's forests contain enormous numbers of trees that have never been cored, never been sampled, never been placed in any database of potential ancient specimens. What those trees might reveal, if studied, is genuinely unknown, and this raises a question that sits quietly at the edge of everything examined in this investigation. Is the current understanding of ancient trees, their maximum age, their geographic distribution there? And this raises a question that sits quietly at the edge of everything examined in this investigation. Is the current understanding of ancient trees, their maximum age, their geographic distribution, their biological mechanisms of survival, shaped as much by what has been studied as by what actually exists? The record reflects the specimens that researchers happen to examine, in the locations they happen to visit, using the methods that happen to be available at the time of examination. That record is real and valuable, but it is also partial, and a partial record, presented as though it were complete, creates a distorted picture, not through any deliberate act, but simply through the natural limits of what any investigative effort can cover. Some believe the current record is close enough to complete that the missing pieces would not significantly change the overall picture. Others disagree, pointing to cases like Prometheus as evidence that the gaps in the record are large enough to matter. Neither position can be fully confirmed with the data currently available, and that inability to confirm, that genuine, unresolved uncertainty about how representative the existing record actually is itself one of the most important unresolved details in this entire investigation. The trees that have been studied are extraordinary. The work done to understand them is serious and valuable. The frameworks built on that work have produced genuine insight into the biological, climatic, and ecological history of the Earth. None of that is diminished by acknowledging that the picture is incomplete. Incompleteness is not failure. It is the normal condition of any active area of scientific inquiry. The concern raised in this investigation is not that incompleteness exists. It always exists, but that it has not been consistently communicated alongside the confident conclusions that rest on top of it. What would a more complete and honest account of ancient trees look like? It would include the age estimates, as it does now, but it would also include the uncertainty ranges that surround those estimates, stated clearly rather than buried in technical footnotes. It would distinguish between age estimates produced by direct ring counting and those produced by growth rate projection, and it would communicate what that distinction means for the reliability of the number. It would clearly separate the age of root systems from the age of visible trunks when those are different things, and ensure that distinction travels alongside the estimate rather than being left behind. And it would acknowledge, explicitly, that the inventory of ancient trees is incomplete and that the current record reflects what has been examined rather than what exists. That kind of account does not currently reach most people who encounter this subject. The version that reaches them is cleaner, simpler, and more confident. It is built from the same research, but with the rough edges smoothed away. And those rough edges, the uncertainties, the limitations, the unresolved questions, are not decorative details. They are part of the actual content of what science has found. Removing them does not make the account more accurate. It makes it less so, in a way that is difficult to detect from the outside. These trees have stood through everything, through periods of history that left no written record, through environmental changes that reshaped the landscapes around them, through the long silence of centuries, during which no human being had any awareness of their existence or their age. They were ancient before the concept of measuring age in the way that modern science measures it had ever been developed, and they will likely continue to stand long after the current debates about how to measure and interpret their records have been settled, revised, and settled again. They contain a record that humans are still learning to read, and perhaps the most important thing that can be said about that record, after this careful and extended examination, is that the reading is still in progress. The methods being used to read it are good, but not perfect. The specimens available for examination are remarkable, but not complete. The frameworks built on the readings so far are valuable, but carry inherited uncertainties that have not been fully traced or fully communicated. And the questions that remain open about age, about location, about the reliability of the data, about what the full inventory of ancient trees might reveal, are not minor technical details awaiting routine resolution. They are genuine open questions at the heart of a subject that matters more than most people realize.